Dr. S. Henrique Faria. So may I request you, sir, to present on mountain glacier and snow in a changing climate. Please turn on your mic, cam on, and share your screen. Thank you so much.
Hello, good morning. I'm Sérgio Henrique Faria. Can you hear me?
Yes, of course, loud and clear.
Perfect. Okay, so I will start then. Let me share the screen. Okay, share screen, lecture, and share. Okay. And then let's start. I'm not sure. Are you seeing my slides? Is it okay? I can't see from Zoom. I can't see if it's okay. Could you please confirm that you see my slides without problem?
Yes, yes, okay, we can see.
Perfect. Then I will continue. So then good morning, everyone, or good afternoon, good evening. As I said, I'm Sérgio Henrique Faria. I'm a Ikerbasque professor in the Basque Center for Climate Change in Bilbao. That's in the Basque country, northern Spain. And I will talk to you today about mountain glaciers and snow in a changing climate. The outline of this lecture is this. The idea is to present you the latest results from the IPCC report, the 6th assessment report, AR6, the contribution from Working Group 1, which is the physical science basis to the IPCC report, the Intergovernmental Panel on Climate Change. And I want to present and discuss the main conclusions of this report regarding glaciers and snow in a changing climate. And for doing that, then we will see first the current state of the climate, then analyze possible climate futures, and finally check the regional information we have for different regions around the world. And well, that will be it. Then I will just mention the references, which are basically the sources from the different sources from the IPCC. So let's start with the IPCC report. I can see the time. Let me take here the clock. Okay. Yeah. And well, as you see, the contribution of the Working Group 1 to the 6th assessment report of the Intergovernmental Panel on Climate Change. This is the cover. It has been published or in non-formatted version. The final formatted version will come later on, but the non-formatted version has been published some weeks ago, and it involved 234 authors from 65 countries. The gender balance was about 28% women and 72% men. And one interesting thing about this 6th report is that 63% of the authors were first-time authors for the IPCC assessment. You may know that the IPCC report cycles, so this is the 6th cycle, Each cycle consists of 3 assessment reports belonging to the 3 working groups: Working Group 1, Working Group 2, and Working Group 3. First, it comes the Working Group 1, which is this one. It addresses the physical basis, the physical science basis. Later on in 2022, the other 2 working groups will publish their assessment reports that will address impacts, adaptation, and mitigation of climate change. So in this physical science basis assessment report, we pass through several years of work and through several review cycles. And at the end, we had more than 78,000 review comments, and we have to address every one of them. 46 countries commented on the only one of the final government distribution. We have several drafts that are reviewed. We have the first order draft, the second order draft, and then the final government distribution. Only on the final government distribution, we had 46 countries commenting on the report. And then as the result of all this process, we have the report, which assesses more than 14,000 scientific publications, mostly of them recent publications within the last 5 or 6 years. So, and what are the main conclusions of this report for mountains and snow, or glaciers and snow on mountains? Then we go to the current, first, the current state of the climate. What are the conclusions from the report concerning the current state? We start first with general, that is global conclusions. And the report, in fact, the summary for policymakers, as you can see here, it starts with the statement A1. So the very first statement of the summary for policymakers is that it is unequivocal that human influence has warmed the atmosphere, ocean, and land. Widespread and rapid changes in the atmosphere, ocean, cryosphere, biosphere have occurred. So cryosphere here is important to notice. So what is the importance of this statement? So the reports, we are in the 6th one. The reports, of course, started with the first one in the 90s. And so we have decades of reports and assessments. And at first, it was suspected that humans had an influence on climate. And this suspicion evolved with every report, with more evidence, with more studies. And in this 6th report, it states that it is unequivocal. So it's certain. There is no doubt at all, it's beyond doubt, that human influence has warmed the planet. That's the fundamental conclusion from here. So the second important conclusion comes the statement A1, 8.1.2 is that each of the last 4 decades has been successfully warmer than any decade that preceded it, since 1850. 1850 is referred as the, that's the reference year, or the year referring to the pre-industrial, or the transition from pre-industrial to industrial period. So it's let's say, so of course the industrial revolution was a continuous process. It's not just in 1 year you have industrial revolution, but we have to set a reference. And as reference, often, not exclusively, but often, the Industrial Revolution is defined as 1850 as the reference. So everything before 1850 is then called pre-industrial, and everything after 1850 is called industrial period. So that's the idea, that since the beginning of the industrial period, each of the last 4 decades has been successfully warmer than any decade before. Another global statement is that, so quantifying this warming, global surface temperature was 1.05 degrees Celsius higher in the last decade, the decade of 2011 to 2020, than the reference decade from 1850 to 1900, with larger increases over land. So we have more than 1.5 degrees Celsius warming over land during the whole industrial period, than over the ocean, where we had a warming of less than 1 degree, so 0.88 degrees Celsius. So this tells us that the planet has warmed more than 1 degree Celsius since the Industrial Revolution, and that land has warmed more than ocean. And this warming might seem small, 1.09, or better, over land 1.6 degrees Celsius, but every half degree, so every 0.5 degrees Celsius has a very important impact on climate. It changes the intensity of extreme events. It changes the behavior of the climate in different regions. So a warming over land of more than 1.5 is a very important change for the climate. Here is how this warming, or the causes of this warming, what we see on the left, called observed warming in gray, is this statement that we saw before, a warming of a little bit more than 1 degree Celsius, as indicated by the top of the gray bar. And this is the observed warming in the decade 2010 to 2019. We always take a decade or so because we have to average. Of course, 1 month or 1 year of temperature doesn't tell us much about climate. We always have to increase the period to have an average to reduce the effect of natural variability of the climate. Yeah. And so this is relative to the Industrial Revolution period reference, which was here at 1850 to 1900. So the temperature averaged over this period is the reference, and the warming in relative to this reference was a little bit more than 1 degree. And what were the causes of this? And here we see that the total human influence is essentially the whole warming. And this can be split in well-mixed greenhouse gases. These are mostly, we will see CO2, that is carbon dioxide, but also methane and other greenhouse gases. And then we have a cooling, because as you see, the greenhouse gases, they in fact would generate a greater warming, global warming of 1.5 degrees Celsius, but what we observe is a little bit more than 1 degree. And that's because there is also a cooling from other human drivers, like, as we will see, aerosols and so on. And then they compensate a bit of the warming from the greenhouse gases and produce the net effect of 1 degree Celsius. And then there are negligible effects, as you see here. They are around 0. For instance, solar and volcanic drivers, and the internal variability of the climate. When we average over these periods, then we will see that the contributions are so. Now, if we go even more detail, we will see that for the warming, the red part, carbon dioxide is the major contributor to global warming, contributing to almost, well, something like 0.3 well, 0.8 more or less degrees Celsius equivalent of warming. Then we have methane, which contributes also around 0.5 degrees Celsius equivalent warming. And then we have smaller contributions from nitrous oxide, halogenated gases, and volatile organic compounds and carbon monoxide. They are contributors for warming, as well as black carbon. But then, of course, we have the cooling that we saw here, other human drivers, and the major cooling effects come from sulfur dioxide and nitrogen oxides. They are aerosols that produce major cooling. So we do all this balance and concludes then that it's clear that from all these contributions that the human influence is decisive on warming. Now that we understand more about warming, let's go to the next important statement is that are still global. In 2019, I'm sorry. I'm getting some warnings here. Let me just dismiss this. In 2019, atmospheric carbon dioxide concentrations were higher than at any time in at least 2 million years. And we have high confidence on that, high confidence that carbon dioxide concentrations were higher or are higher actually than at any time in at least 2 million years. And concentrations of methane and nitrous oxide were higher than at any time in at least 800,000 years. Again, with very high confidence. So these concentrations that cause global warming are with high and very high confidence, unusual in the long term of the history. So now let's go to mountains and snow. That's the key. How we translate this global information into glaciers and snow on mountains. So the first, more general, the current states that with few exceptions, mountain glaciers have retreated since the second half of the 19th century with very high confidence. So we have seen a general retreat of glaciers worldwide, with few exceptions. And this retreat has occurred at increased rates since the 90s. So that's very important. So we observe a retreat since the second half of the 19th century. And this is already a cause of worry because the second half of the 19th century, as we have seen, is the beginning of the Industrial Revolution. So we are talking about industrial period and the retreat of all glaciers, or almost all. And more worry is that this retreat has increased in its rates since the 90s as a reflection of global warming. And human influence is very likely the main driver of the global retreat of glaciers since the 90s. So this accelerated retreat of glaciers that we have been observing since the 90s is very likely caused by human influence. So very likely is, I would say, it's a very strong statement. This means that the scientific community is quite sure, quite confident that human influence is the main driver of global retreat of glaciers since the 90s. And also, the human influence has very likely contributed to the decrease also in the spring snow cover in the northern hemisphere since the 50s. So we have a reduction in spring snow cover and a general retreat of glaciers since the 90s, and both effects, which are crucial for the water supply and for the snow and ice cover, they are both very likely related to human influence. These are important observations of the current state of the climate in mountains. Also, the global nature of glacier retreat with almost, so what we mentioned before, that almost all of the world's glaciers are retreating synchronously. Since the 50s is unprecedented in at least the last 2000 years. Here we have confidence of that, it's a medium confidence, so it's not absolutely certain, but most studies indicate that this general global retreat that we have mentioned, at least since the 50s, is unprecedented in at least the last 2000 years. Again, talking about the retreat of glaciers and in particular some regions. Now let's start to go a bit more regionally, but not in a specific region, but warming has occurred in the Himalayas, in the Swiss Alps, and the Central Andes, and has increased with altitude. That's very important and a cause of worry. This is called elevation-dependent warming, which means that we have the usual warming that we see on the surface of the planet, the global warming that we already mentioned. On average, over land, I already mentioned 1.59 degrees Celsius over land. But then in these regions, Himalayas, Swiss Alps, and the Central Andes, the warming as you go up on the mountain is faster. That is, we are not having just the 1.59 degrees warming, we have higher warmings, and this warming, so it gets the difference or the increase in temperature since the beginning of the industrial period. The increase in temperature is greater the higher you go in the mountain. So on the top of the mountains in these regions, we measure higher values of warming, 1.8 degrees Celsius, 2 degrees Celsius, 2.5 degrees Celsius of warming in different altitudes, in different elevations in these regions. So the top of the mountains are warming faster than the rest of the planet. This is called elevation-dependent warming. It doesn't occur everywhere. It occurs in certain regions, not just a few. Many regions show elevation-dependent warming, but not all. But the most crucial are the Himalayas, Swiss Alps, and the Central Andes. This has implications because it leads to faster changes in the snow line, in the glacier equilibrium line altitude, and the snow-rain transition height. And we have high confidence on that. So this means that since the beginning of Industrial Revolution, we are observing, especially in these regions, this kind of effects of changes in the snow line. The equilibrium line for glaciers, the altitude of the equilibrium line is increasing, and the snow-rain transition height is also increasing. And these are observations which are particularly clear or striking in these regions, Himalayas, Swiss Alps, and Central Andes, where elevation-dependent warming is most evident. Continuing, we also say that global warming induced earlier onset of spring snows melt and increased melting of glaciers have already contributed to seasonal changes in stream flow in low elevation mountain catchments, and we have high confidence on that. So this means that all this warming that we have been talking about and the retreat of glaciers, which implies, of course, melting and the reduction of the snow cover, these all cause additional melting, and this additional melting is causing seasonal changes in stream flow. These are all the observations. These are proven observations of changing climate. But now let's go for, okay, that's what we know now about globally about the current climate. what is the future of the planet? And then I will go to particular regional information. So based on these observations that I have mentioned, what can we expect for the future of mountains, in particular the glaciers and snow on mountains? First, again, going globally, global surface temperature will continue to increase until at least the mid-century, so until at least 2050, under all emissions scenarios that are considered in the report. This assessment report, the sixth assessment report, considers 5 emission scenarios. These emission scenarios are possible situations of CO2 emissions and other greenhouse gas emissions by humanity, from very low emission, a very optimistic scenario, to high emissions, which are what we call business as usual, which is the rate of emissions, yearly rate of emissions that we have right now. If we continue to emit just as we are emitting now, that would be the pessimistic scenario. And then we consider 5 different... Sorry?
Professor Faria, 5 more minutes. 5 more minutes. Gentle.
Oh, okay. Please. Okay, I started later with my chronograph, and then I thought I had a bit more. I will go then a bit faster. Thank you. So, as I was saying, this global warming will exceed the limit that we would like to have of 1.5 degrees or 2 degrees Celsius proposed by the Paris Agreement. We will exceed this limit during the 20th century, unless we do very deep reductions in CO2 and other greenhouse gas emissions. So I will go faster a bit here. This was just, back to show you, these are the 5 emission scenarios. And this is the result of global surface temperature by the end of the century for the 5 different scenarios, where we see in dark shade the current global warming, slightly above 1 degree Celsius, and the additional warming until the end of the century for the different scenarios. And what you see at the sides in the other bars are the contributions from carbon dioxide, non-carbon dioxide greenhouse gases, and aerosol. And then you can compare the different contributions, and you see how pessimistic is with warmings with more than 4 degrees Celsius warming in the most pessimistic scenarios by the end of the century. So what this implies for the futures of glaciers, that additional warming is projected to further amplify permafrost thawing and loss of seasonal snow cover, of land ice and of Arctic ice, and this with high confidence. Another implication for the future is that mountain and polar glaciers are committed to continue melting for decades or centuries with very high confidence. This means even if we reduce emissions right now, because of the inertia of the process of melting glaciers, they will continue to melt for decades or centuries. So why reducing the emissions then? Because if we don't reduce, the melting will even accelerate, and then it will continue for many centuries more. So the sooner we reduce the emissions, the sooner we will reduce the melting. And hopefully, after many decades or centuries, this melting may stop. But we cannot expect that the global melting of glaciers will stop tomorrow. No, it is already defined by the inertia of the glaciers. It will continue for decades or centuries. And loss of permafrost carbon following permafrost thaw is irreversible at centuries, centennial time scales. It's also virtually certain that snow cover will decline over most land regions during the 21st century in terms of water equivalent, extent, and annual duration. Again, this has to do with the whole inertia of the whole climate, the atmospheric, the process of atmospheric circulation, humidity, and the warming of the land use, land cover. All these things imply that snow cover will continue to decline in most land regions during the 21st century. Also, extreme precipitation is projected to increase in major mountainous regions with medium to high confidence depending on location, with potential cascading consequences of floods, landslides, and lake or outbursts in all scenarios. So even the most optimistic scenario will imply extreme precipitation increasing and causing more floods, landslides, and lake outbursts. And projected runoff.
Sir, I intervene. Dr. Abid, please give him 5 or 10 minutes more, and we can accommodate this time when the delegates present. 2 or 3 delegates are not present, so we can make
Thank
up the
you.
time.
Thank you very much. I'm taking care of the time now. Thank you very much.
No, please. I'm requesting Dr. Abid to give you 5 or 10 minutes more.
Okay, sure. Please go ahead, Professor Faria.
Thank you very much. Yeah, I apologize for this. So just to finish, then projected runoff is typically decreased by contributions from small glaciers because of glacier mass loss, while runoff from larger glaciers will generally increase with increasing global warming levels until their mass becomes depleted. What does it mean? It means that the small glaciers, they will not in the future contribute so much to the runoff simply because they are becoming too small, and then their melting will not contribute so much. But the large glaciers, because of the accelerated melting, they will contribute to runoff, increasing global warming and increasing also with increasing global warming and increasing runoff. So small glaciers will reduce their runoff, but larger glaciers will increase runoff until they become small glaciers. So finally, finishing with regional information. Here what we have is a map of the mountain regions around the world. And I will go through these regions with the particular conclusions from the assessment report. First, with Rocky Mountains and Alaska in North America, region 1 here in red, reduction in glaciers, seasonality of snow and ice formation, loss of shallow permafrost, and shifts in the rain-snow transition line are all projected to alter the seasonal and geographic range of snow and ice conditions in the coming decades. So we expect in the future that the snow and ice conditions in Alaska and Rocky Mountains will change because of reduction in glaciers and the seasonality of snow. And also, continued shrinkage of glaciers is projected to create further glacial lakes in the Rocky Mountains and Alaska. Then we go to South America with the Andes, glacier volume loss and permafrost thawing in the Andes will likely continue, causing important reductions in river flow and potentially high magnitude glacial lake outburst floods. So for the Andes, this is a serious preoccupation, a serious worry for us that the glacial lake outburst floods are expected to increase because of glacier volume loss and permafrost thawing. In the Scandinavian mountains in the high north of Europe, most periglacial debris flow processes are projected to disappear by the end of the 21st century, even for low warming scenarios. Then in the European Alps, elevation enhanced, we already mentioned that before.
Excuse me, Professor Faria, take your time. Please go slow. We have allocated 10 minutes to your present, extra 10 minutes.
Okay, I will go a bit slower.
Participants are taking a lot of interest, so please take your time.
Yes, good. So, as I already mentioned before, in the European Alps, we have the elevation enhanced warming. There are regions like the European Alps, the Andes, and also the Himalayas. And this elevation enhanced warming with on the long term, it implies an elevation enhanced long-term trends in maximum near surface air temperature and diurnal temperature range. And well, as I said, these were observed in Swiss Alps, and this caused that snow cover will decrease below elevations of 1,500 to 2,000 meters throughout the first century with high confidence. And a reduction of glacier ice volume is projected also with high confidence. What does this mean? This means that snow cover in elevations up to 1,500 or 2,000 meters, the snow cover is expected to decrease because of elevation enhanced warming. Why this limit of 1,500 to 2,000 meters? Because the atmospheric circulation above this high, above 2,000 meters, it changes differently. It gets more moisture. And then in some regions above, within the Alps, I'm talking in the European Alps, above 2,000 meters, in some regions of the Alps, some mountains may even increase the precipitation of snow because of more humidity, more snowfall in these very high regions above 2,000 meters. But below 2,000 meters, because of warming and the usual near surface atmospheric circulation, we have high confidence that the snow cover will decrease in general in the European Alps. So below 2,000 meters, snow cover will decrease. Above 2,000 meters depends on the mountain, depends on the particular place in the Alps. Some regions may have more snow cover. However, glaciers in all heights, even in the higher elevations above 2,000 meters, they will continue to reduce their volume. Why? Because even in those mountains, very high mountains with increased snowfall above 2,000 meters, the melting and the flow of the glacier overcome the additional snowfall in the high altitudes. So it's a complicated conclusion here, so I will summarize. In the lower altitudes, so below 2,000 meters, snow cover in general in the Alps will decrease. Above 2,000 meters, it's different region to region within the Alps. Some will increase in snow cover, others will decrease. But in all regions, reduction of glacier volume is projected. So Caucasus and Pontic mountains, what we see is that mountain permafrost degradation at high altitudes has increased the instability of mountain slopes in the past decade. So that's the observation that we have seen. So slopes are getting more and more unstable and prone to landslides because of the degradation of permafrost. In the East African mountains, what we see is that African snow and glaciers have very significantly decreased in the last decades. And this trend will continue over the 20th century with high confidence, no matter the scenario. So even in the most optimistic scenarios, so the future for African snow and glaciers is dark, is difficult. So they will continue to decrease. And high mountain Asia, what we see here, there are several conclusions, of course. Snow cover has reduced since the early 20th century, and glaciers have thinned, retreated, and lost mass since the 70s with high confidence. These are observations. Although, of course, we know the Karakoram glaciers, they are a kind of interesting exception. They have either slightly gained mass or are in an approximately balanced state. Here we have medium confidence, and it's not clear yet if this process in the Karakoram glaciers is just a transitory process or is a longer term process. We are still investigating that. But the Karakoram glaciers are a clear exception in the high mountain Asia region, because the rest of high mountain Asia is losing clearly a lot of mass in glaciers. Snow-covered areas and snow volumes will decrease during the 21st century. Snow line elevations will rise with high confidence, and glacier mass is likely to decline with greater mass loss in higher greenhouse gas emission scenarios over all the high mountain Asia. And finally, in the southern Alps in New Zealand, what we observe is that glacier ice volume in New Zealand has decreased in the last decades. So these are the main conclusions also in the regional level from the current assessment report. Impacts and other regional economic, socioeconomic impacts will be reported in the coming assessment reports in 2022. So wait for the next 2 reports. In the meanwhile, I recommend you to visit this page, the interactive atlas of the IPCC, where you can analyze the future of different regions in the world. What we have here is an example of the interactive atlas. You can go there, click, select different regions, and see different data as this one. These are stripes showing the evolution of, as we see here, mountain snowfall change. So how much snowfall in mountains is changing over the years since 80, 60, so 1940 or 1950s, yeah, it's in the middle, since 1950 to 2100, so past and future, relative to the beginning of the Industrial Revolution, how snowfall has changed and is projected to change in the different months of the year. So every line here is 1 month, and every vertical column is 1 year, and the values are shown in this column of the snowfall change. So everything brown is less snowfall, everything blue or green is higher snowfall. And we see that until more or less the 90s, there was some variability, natural variability and so on, but no clear change in the snowfall, except maybe in the summer where the snowfall was slightly reduced. But since the 90s, in this region here, which is the region including the Himalayas, we see that especially in the summer period, snowfall has reduced and is projected to reduce dramatically until 2100. And here is how to select different regions and different variables and periods on this page. So try it. It's a lot of fun from the scientific point of view, of course, from the human point of view and social point of view. To see gloomy futures is not fun, but as a scientist, it's very interesting to see all the data that you can extract and learn from the interactive atlas. Thank you very much for your attention. These are the main sources of the data in this lecture. And I apologize to the lecturer, the next lecturer, for taking a little bit of his time. And thank you very much for the extra time, and thank you all.
Thank you very much, Professor Faria. Very informative wealth of knowledge was there in this presentation, and you can see the comments of our participants. All of them are actually appreciating your presentation. Thank you so much.
Thank you very much.
Okay. So our next faculty member is Dr. Mohinder Silaria, Associate Professor, Government College, Champa, India. So please, you